and when I'm done, the recording will be available in the announcements as well as in the weekly overviews. So let me share my screen here. So I always post a link to the recording after the class is over, as soon as the system sends it to me. And then I've also been putting the links in the weekly overviews. So you'll see a link to the recorded class meeting for Thursday once I get the link from the Microsoft Streams app, generates the links and sends it to me. And then once I have it, I'll post it. Any questions on that? Okay, so I would ask if you try using the links and you have any difficulties, let me know. One thing I know for sure is that you have to log in through Office, if I'm not mistaken, with your RPCC email and password, your student email and password. And then you can access the apps through Outlook and go into Streams, not Teams, Streams, and it shows the listing of videos. And you should be able to get into it that way. But let me know if you have difficulty, because there's something that I've been working with on IT on to make sure that you have access. I changed permissions to allow anybody in the organization, which to me means anybody who's attending RPCC or working for RPCC. But I can't access it as a student, so I don't know. So if you have trouble, just let me know about it. All right, so I'm going to go into the weekly overview for work and energy, because that's our task for today. Please don't forget, you have to respond to the energy application activity by 11:59 p.m. on Saturday. It tells you right here to post your answers, no replies needed. I'm going to talk to you about your second bonus today as well. So I'm going to do that actually before we go into the lecture, so that I can answer any questions that you might have about that. Okay. So I'll just do it right here. Let's see. Okay. So this is a gravitation bonus. It's worth 10 points toward the item of your choice, except the project and the overall grade. So you cannot use this to boost your final score in the class, or you cannot apply this bonus to your project. But other than that, you can put these points anywhere you want. So you could break these points up and put, 5 here and 5 there, like maybe one application activity that you missed or a problem set, or you could go back and put it on the midterm, or you could hold it and say put it on the final. You have the option of anything, using this bonus points on anything except the project and the overall course grade. So what do you have to do? So you have to answer these questions. Okay. So you have to use the lecture notes to answer these questions. And then part number 2, you have to complete this worksheet. Okay. So they give you a little bit background here. And when you go to this gravitation website, some of you may find this simulator very familiar, because it is the same one that you used in the lab class. But you are not doing the same thing. So let me show those folk who are not familiar, who may not be part of a lab class. Let me show you how this works. So basically you have these two objects. You can drop and drag them any way you want to. Okay. That changes the distance, which you can measure using this meter stick. The distance between them from center to center, just like the gravitation law says. So you can measure the distance between them using the meter stick. You can increase the masses by moving the slider, or you could click one by one using the arrows. And then let's say you wanted it to put it in scientific notation. See, it's showing you the amount of force between the objects. Okay, so once you know these values, then your task is to work through this worksheet. Okay, now this worksheet is worth, says 10 bonus points. So if you complete this worksheet, and let me just see when the worksheet is due, when this bonus is due. Let me open up another weekly overview here.
Miss Xenon, I'm having trouble seeing what's going on. If the screen is saved or not, I'm just having an easy zone.
Can you see this screen right here?
No.
That's the weekly overview. So normally can you see that?
No, I can't see anything. All I see is a black screen with a circle that says EZ on it.
Okay, I am sharing. I'm in screen sharing mode. Let me stop sharing. Okay, and let me share again. Okay, and okay, can you see that now?
Yeah, I can see it now.
Okay, I don't know what happened there. Were all of you in the same situation?
Yes, man.
Y'all couldn't see the screen?
Yeah, I couldn't see it towards the end.
So you guys, I'm talking and explaining something to you, and you couldn't see the screen?
Yeah, I was taking notes on it though. I was going in and out thinking there was something wrong with my end.
What about everybody else? Were you in the same position where you couldn't see the screen?
Yeah, I thought there was something wrong with my camera or something.
Okay, well, Annette, please speak up when you're having issues like that, because I have no idea, no way of knowing if I'm sharing and you can't see the screen. So, I mean, I was in sharing mode, so I don't, let me backtrack then. It means that you didn't see anything that I did.
That's correct.
Wow, okay. All right. So again, I'll just remind you that, I post links to the recordings in the announcements and in the weekly overviews. I'll post the recording for this one after we're done. And then, so go into the work and energy overview. Can you see that now? Hello?
Yes.
Okay.
Yes.
All right. So you have to respond to the energy application activity by Saturday, 11:59 p.m. You post your answers. You don't need to reply to classmates, as the directions here tell you, as well as if you go into the forum, it just tells you post your answers, no replies needed. But you do have to post your answers by 11:59 p.m. on Saturday, or you won't get credit for it.
Okay.
All right. So what I started doing was explaining the second bonus. So I'll open that up again. Okay. So this is the gravitation bonus. Y'all can you see that?
Yes.
Okay. I have no idea what happened, why the sharing didn't work the way it was supposed to the first time, because I'm doing the exact same thing. But I'm glad we were able to get everybody on the same page. Please, if we're having technical issues, let me know, because it's like we're in different places, right? So
Right.
yeah. Okay. All right. So this bonus is worth 10 points toward the item of your choice, except the project and the overall course grade. So you can use those 10 bonus points to change the score or improve the score on any item except the project and your overall course grade. So like if you wanted to go back and put the 10 points on your midterm, that would be fine. Just let me know. If you wanted to put the 10 points on your final exam, let me know. If you want to put 10 points on problem set number 8 because you missed it, let me know. However you want to use the points. When you turn this in, you just write in the upper right corner what you want to put the bonus points on. If you don't put anything, it automatically defaults toward the final exam. Okay, so the first part of this is basically just answering some questions about gravitation. They shouldn't be overly challenging to you. Some of them you might have seen before, but again, just answer them. Use your lecture notes to go back and answer these questions. And then part 2 is where you're going to be using the Gravitation Simulator. There's some background here regarding gravitation. The main thing is you want to click this link. And when you click that link, it opens up this simulator. Some of you have probably seen this simulator because it's the same one that you use to do the gravitation experiment in lab class. And so for those people who don't know, who don't have lab, let me just give you the benefit of showing how this works. So you can move the objects M1 and M2 closer or further apart. You measure their distance using this meter stick. Notice I put it on scientific notation and it calculates the force for me. Tells me the amount of force that each object is pulling on the other object with. And it's nice to see it written this way as opposed to all those zeros for me. This is more compact and easier for me to comprehend. And then you can change the mass by sliding it or changing the mass by 1 by using the arrows. Do any of you have questions about how this simulator that you're going to use to do the bonus works? Okay, so once you have gone into the simulator, then you're going to use it to complete this handout. There are 10 questions there, and so you need to answer all 10 of those questions. Actually, just as a heads up, what I typically do is if you complete part 2, I give you 10 points. And if you complete part 1, I give you additional 5 points. So actually, you'll have 15 bonus points. So just, I say 10 to try to, spark your interest. But maybe 15 will really get you to make an honest effort to do this and earn those bonus points. And also get some great practice with gravitation. Any questions on that? All right. So what I was doing before you guys let me know you weren't able to see the screen was I was about to go and click to see when you have to turn this in. So just bear with me so that way you know when it's due. So it's not due next week. So you have until the 23rd of April to turn in that second bonus. All right. Any questions on that? All right. So let's get into the energy notes. Okay. So the whole goal of this notes is to expose you to the concept of work and energy. We'll take a brief look at this idea of energy resources, but really and truthfully, I don't spend too much time on that because the third bonus that you're gonna have access to deals with this whole notion of energy resources. So one of them at least. So I'll briefly mention those things, but we won't spend too much time with it. All right. So work and energy in everyday life. So we've come across this concept before, that words and vocabulary that we use in conversation doesn't always match the physics definition of those words. So words like work and energy we use in conversation for, everyday just talking purposes, but when we use those words in physics, they have very specific meanings, and we have to be careful to use them properly when we're using them in the physics sense of the word. I mean, in everyday conversation, nobody's really critiquing whether you're using those words correctly, but in physics, yes, we have to be very specific because those words have very, very specific meanings. And so that's what we're going to be focusing on. What is the physics definition of this work and energy and conservation of energy and that kind of thing, right? So here is the definition of work: the transfer of energy by a force that causes an object to be displaced. So you have a force that's acting on an object and it moves that object or causes it to be displaced, then work is done because energy is being transferred during that process. You apply a force to an object, it moves, energy is transferred, work is done. And so if we want to put a formula with that definition, we can say that work W is equal to force times displacement. Now, let's be careful because for two things. Please do not mix this W up with the W that we use for work. For weight. Okay? The W that we use for work is a scalar property, meaning we don't have to have direction, right? Size only. While the W that we use for weight is a vector. So we have size and direction that goes with that. In addition, weight is found by taking mass times gravity. So if you are trying to find work and you do mass times gravity, you're going to be missing some parts of the formula. So pay attention to that. This is why it's important to understand context. It's important to understand the different properties. And they show you just below the formula, force times distance, the unit that goes along with work. To get work, you have to multiply a Newton times a meter. And when you do that, you combine those two to get the new SI unit, joules. So work is measured in joules, and 1 joule equal 1 Newton times 1 meter. There's also something else that you need to pay attention to when using this formula. And that is, it tells you the force and the displacement have to be in the same direction. Now, let's try to visualize what's going on there. Let's say you're applying a force to an object and you're pushing it. Let's say you have a box that's sitting on a tabletop. And you walk up to the box and you push it. And your force is in the same direction as the box is moving. So you're pushing forward, the box is moving forward. So your force and your displacement are in the same direction. Or let's say you attach a rope to the box and you lift it up and the box moves up. So your force is up, the box moves up, So your force and your displacement are in the same direction. So work is being done. So you might ask the question then, well, is there a situation where you apply a force to an object, it moves, because how can you get zero work? Well, obviously, if you don't apply a force, then you aren't doing any work. Also, you could apply a force and the object not move at all. So the displacement is zero. You're not doing any work. But is there a situation where you have a force and you have a displacement, but the work is still zero? Yes. So if you carry an object, that's the situation where the work is going to be zero. How does that happen? Well, if you're carrying an object, you're holding it and supporting its weight. So which way does the weight of an object point? Down. So your force to support it has to be up. But if you hold the object and you walk forward, the object is moving forward, but the force you're applying is up. So in that particular situation, the force is up, but the object is moving forward. So the force and the displacement are perpendicular to each other. If the force and the displacement are perpendicular to each other, when you carry an object, the work done is zero. So, see, this is the difference between work every day and work in physics. Because let's say, for example, you worked in a warehouse and your job was to carry boxes all day. You wouldn't want your employer to come and say, well, you carried the boxes. You didn't technically you didn't do any work, so you don't get paid. No. See, that's the difference in everyday in physics. But in physics, if you're carrying an object, you're not doing any work, technically. Okay? So, if you're working in a warehouse and you're getting paid by the physics definition of work, push the boxes. Don't carry them. Okay? So, again, work is force times displacement. That force and that displacement have to be in the same direction. And the new unit, the SI unit for work, is the joule. 1 Newton times 1 meter equals 1 joule. Let's talk about this work energy theorem just briefly. Now, before we go into the work energy theorem, there actually should be another slide in this whole packet that defines for you what is kinetic energy. And some of you might know because you've dealt with kinetic energy before. And some of you might know because I gave you the formula in lab class to do the energy experiment. But for those of you who have not been exposed to the idea of kinetic energy, we use the symbols KE for kinetic energy. Capital K, capital E, kinetic energy equals to 1/2 mv squared. 1/2 mv squared. 1/2 mass times velocity squared. So the first part of this equation on the right hand side, 1/2 mv squared. That's kinetic energy, and it is measured in joules. Kinetic energy is measured in joules. So work and kinetic energy are both measured in the same units, so there's definitely a connection between them. And that's what this work energy theorem is all about. So it says that the net amount of work done, W net, we understand that concept of net now, because force net means some unbalanced force or, extra. You could think of it that way. So work net done on an object or a system changes its kinetic energy. So the work energy theorem says, hey, if a system is changing its kinetic energy, if an object is moving, because first of all, if it's not moving, it doesn't have any kinetic energy, because V is velocity. If it has no velocity, it has no kinetic energy. So we're not talking about that situation, right? Says if an object changes its kinetic energy, then we have some work done. Okay? So if you do work on an object, net work on an object, then that object is going to change its kinetic energy. And that's what you see there. W stands for work equals to 1/2 mv squared minus 1/2 mv naught squared. Now let me break that formula down for you a little bit more. So W on the left side is obviously, that's work. But what the right hand side is saying is that if you take the final kinetic energy minus the initial kinetic energy, you find out the difference between those two, you find out how much work was done. So 1/2 mv final squared minus 1/2 mv initial squared. Remember, I told you different textbook, different notes, use different notation. So in this one, 1/2 mv squared is talking about the final kinetic energy minus 1/2 mv naught. Remember that subscript 0 is naught, means when the kinetic energy is at the starting velocity. Excuse me. So 1/2 mv naught squared means the starting kinetic energy. Okay. So if you want to know the amount of work done, look at how the kinetic energy changed. Gravitational potential energy. So we've been dealing with gravity quite a bit. And the question then now is, when we want to look at this from an energy perspective, is how does an object change its energy when it's moving under the influence of gravity only? Okay. So we know lots of situations from our studies where objects are moving under the influence of gravity only. So that is a free-falling object. That can be a projectile, a pendulum. Okay, so these are all objects that are working against gravity. And so when that happens, those objects store up potential energy. And we call that gravitational potential energy because work is being done on the object against the gravitational force. So for example, let's say you lift an object straight up. So you got your box again, you lift it straight up over your head. So you're having to do work against gravity because gravity wants to pull that box down, but you're moving it against gravity to move it up. And so in doing that, the box stores up gravitational potential energy. All right. And so if work is done on an object in the vicinity of the Earth, the resulting gravitational potential energy is denoted PE with the little subscript G. That's to remind us that it's gravitational potential energy. And it says this can be thought of as the potential energy put into or gained by the object Earth system, meaning, well, you move the object against gravity, so it's stored up this gravitational potential energy. And they say if an object is lifted at a height h, exactly what I've been saying, right? If you lift the object box up over your head, you move it up higher, so now it has a certain height h. The gain in the object's potential energy relative to the Earth, delta PE, is given by delta PE gravitational, that's what that little G stands for, the change in gravitational potential energy, delta PE with that little subscript G. That's what the symbol delta means, right? The change in gravitational potential energy equals mass times gravity times height. Now, we don't always use the delta in front of it because a lot of times we take the starting height as 0. You can see if the starting height is 0, then that value at the start of potential energy is going to be 0. So a lot of times we just say PE gravitational, or PE with the little subscript G, is equal to mgh. And that's what they're showing here, storing up and releasing gravitational potential energy. So in the picture, so this is like some type of, looks like some type of grandfather clock that has the little bob going back and forth to manage time. And so like there's a chain there, you walk up, you exert a force on the chain. You see the arrow for the force pointing down. So you pull on the chain downward and you move the chain through a distance d, which means that the little mass on the other side goes up a distance d, right? You pull down on the chain to move the little mass m up. And when you move that up, you are doing work because you are working against gravity, right? And how much work are you doing? Where you're moving this object that has a mass m, you're moving it up a height h. So in this particular case, what's your force? You're moving the weight m of you're moving the object m, which has weight mg times its height, the distance h in this case. Okay. So what happens when you let the chain go? Well, the object is going to fall back down and it's going to release that energy. So when you pull down on the chain, the object is storing up energy, En. That's what they said, letter E with the little subscript In. It is storing up energy equal to the work being done, mgh. And when you let the chain go, it is losing energy out, mgh. So whatever is stored up, when you raised it up a certain height, it loses when it falls back through that same distance, h. Okay? And sometimes, and this makes sense because if you think about it, one of the, like in grade school, you might learn the definition of energy. And the typical definition given of energy is the ability to do work. If an object has the ability to do work, then there's energy associated with that. Conservative forces. So these are forces that are when you do work in moving an object, because if you're going to do work, you have to move something. So when you do work, it doesn't matter how the object moves. It doesn't matter which path the object takes. You only pay attention to where the object started and where the object stopped. So if a force is conservative, you don't have to worry about what path did it take to get from the start to the finish. You only have to pay attention to where did it start and where did it stop. And if that is the situation, then you are dealing with a conservative force. So a conservative force does work, causes work to be done on an object, if work is being done, remember the object has to move. So in doing that work, you don't have to pay attention to the path. And an example of a conservative force is gravity. So when objects move under the influence of gravity only, when work is done and gravity is the only force being exerted on the object, then energy is going to be conserved. What type of energy is going to be conserved? Mechanical energy. And so what is mechanical energy? That is the sum of kinetic energy and potential energy. So when you add up KE and PE and you get a constant value, then we know that mechanical energy is being conserved. It means that that object is storing up energy or using energy under a conservative force that's being applied. Okay, so that's what they're telling you here. Mechanical energy is defined as the sum of kinetic energy and potential energy when only conservative forces act on and within a system. The total mechanical energy is constant. So it means that the total amount of mechanical energy in your system is fixed. So it means you can't gain any mechanical energy, you can't lose any mechanical energy. So at any point in your system, if you look at the total amount of mechanical energy, it is going to be the same value, constant, fixed. So we typically look at the idea of at the start and at the finish, or initial and final. So that's what they're writing in that second box. Kinetic energy initial plus potential energy initial equals to kinetic energy final plus potential energy final. So if you look at this object at any point, while it's in motion, while it's storing up and releasing energy, mechanical energy, let's be specific there, mechanical energy, you will always get the same total. Sometimes you might have more kinetic than potential, but when you add up the total, you always get the same. Sometimes you might have more kinetic than potential, but when you add them up, you always get the same total, because you can change, what they say, conservation of energy. Energy cannot be created or destroyed. It can only change forms. And so that's what's happening in this conservative system that is operating under a conservative force. So what happens when the system doesn't conserve energy? And this idea of non-conservative forces is actually more realistic, because we know in the real world there are non-conservative forces like friction. And so it says a non-conservative force is one for which work depends on the path. So there's the object is moving, work is being done, but it matters the path you take. So if you move the object moves in a different manner to go from its start to its finish, then it is going to affect the amount of energy within that system. Okay, so conservative forces, it doesn't matter how you get from start to finish. Non-conservative forces, it does depend on how you go from start to finish. Friction is an example of a non-conservative force. And what happens there in a non-conservative system when friction is involved, some of that mechanical energy, remember, mechanical energy is what? Kinetic energy or potential energy. Some of that mechanical energy is going to be changed into thermal energy. And thermal energy we typically think of as heat. So a friction force is a non-conservative force, and a system that operates with friction is going to lose energy or change energy, some of its mechanical energy, into thermal energy. And a lot of times we think of thermal energy as heat, and so that energy is going to be dissipative or be lost in the system. And those of you who are doing the skate park simulation for a lab class, you got to see that exactly when you put that system on one with friction, and eventually all the kinetic energy and potential energy get zapped and are turned into thermal energy, and ultimately the skater winds up stopping at the bottom of the track because they don't have any more energy. All the energy is gone because thermal energy is typically lost in the form of heat. And so that's what they're showing here for the baseball player. The baseball player's kinetic energy is converted into thermal energy and sound by the force of friction acting through the distance he slides. So this baseball player is stealing a base, for example, and they go into a slide and they move through a distance d. There's friction between the player and the ground while they're sliding, and they show you the friction force. And we know that if the slider is moving to the left, the friction force has to be to the right, because friction always opposes motion. Okay? And so in this particular case, work is done because there's a friction force being exerted, and the player is moving through a distance d. Now, notice in this picture, the friction force and the distance are opposite to each other, so the work done is going to be negative. And so since this work is negative, we can think of it like this. Since this work is negative, in this particular case, we're going to be losing some energy because there's a friction force involved. Okay? So, if these non-conservative forces like friction can do work, how do we figure out the amount? Well, we're looking at this from a perspective of conservation of energy. Of course, we could figure out the work done by the non-conservative force simply by multiplying the friction force times the distance, or the displacement, excuse me. Okay? And so, but we want to look at how we can determine the work done by a non-conservative force through the lens of conservation of energy. Okay? And so what they're doing here is that they're saying that the amount of work done by this non-conservative force can be found by modifying the conservation of energy equation. So you see in the box on the left-hand side, now we don't just have KE initial and PE initial. We also have to add in this work done by non-conservative forces. On the right-hand side, we still have the same thing, KE final plus PE final. And so now we can do a little bit math, there, and to find the work done by a non-conservative force, we just look at the change in kinetic energy plus the change in potential energy. So the work done by our friction force, the work done by our non-conservative force is equal to the change in kinetic energy plus the change in potential energy. See, this is where delta becomes important, because delta KE means KE final minus KE initial. Delta PE means change in potential energy. And we know to get the change, we take what? Our final value minus our initial value. So in other words, they solved this so that they could get this by itself. What happens? If we want to get WNC by itself in this equation, we have to subtract the initial kinetic energy on this side and subtract the initial potential energy on this side. So in every case, we have final minus initial. Final KE minus initial KE, final potential energy minus initial potential energy. Okay? So we have a way, even when there are non-conservative forces involved, to figure out how much are we losing to these friction forces. And so therefore we can write the law of conservation of energy in a more complete way by saying that kinetic energy initial plus potential energy initial plus the work done by our non-conservative force like friction plus OE initial, and OE means other forms, any other forms that we of energy that we have. And there are many different forms of energy. Thermal energy, there's chemical energy, electrical energy, nuclear energy. So if you have any of those types of energy involved in your system, if you account for all of the energy that you have at the start, all of the different types or different forms, then when you look at your system at the end, KE final plus PE final plus OE final, you must always get the same amount of energy total. So that's what it says, that energy may change in form or be transferred from one system to another, but the total amount of energy always remains the same. So this total energy is always constant. Total energy is always constant. Okay, so no matter where you take a snapshot of the system at, where the object is in its motion, if you can capture all of the various energy sources, the total that you start with is going to be the same total that you finish with. Efficiency looks at, well, how much bang do I get for my buck, so to speak. So efficiency looks at how much energy did you put into the system and how much work did you get out. So work out divided by energy in. You're putting energy into the system in order to get some work out of the system. The ratio of work out to energy in tells you about its efficiency. And it says, since for real world processes, W out is always less than E in, efficiency is often expressed in a percentage. And so it's kind of, in a way, if for those of you in lab, you know, we do percentage error. And when we do percent error, we are comparing our value to a known value. In this particular case, you're comparing your work out to your energy in a percentage. And so they just give you some ballpark figures of efficiency for various processes and devices. Notice, for example, the electric motor has the highest efficiency, 98% efficient. That is pretty good. That also explains why we want to go to electric cars as opposed to our gasoline engine cars, if you look, that only get about 30% efficiency. Or diesel engines, because there are many vehicles that are diesel engines, 35% efficiency. So, you know, the more efficient we can get, the more bang we get for our buck, so to speak, then, you know, that's a good thing. More workout per energy in. And then power. Power is defined as the rate at which work is done. And y'all remember from early discussions in the class, I told you, whenever we use that word rate, it means that time is involved. And so, in this particular case, we're looking at the work per unit time, the work done per unit time. So, this is a new variable, a new property, if you will. Don't mix this P up with momentum, right? Because we use the letter P for momentum as well. So in this particular case, they're using the capital letter P. to represent power. And to get power, you take the work done by the time. So if we have a new property, we have to have a new SI unit. The SI unit for power is the watt, like your 100-watt light bulbs. So they tell you that 1 watt is equal to 1 joule per 1 second. A joule that comes from work divided by a second that comes from time gives us a new SI unit, the watt. Okay. And a lot of times when I write out the unit watts, I just spell it out, W-A-T-T or W-A-T-T-S. That way I don't have any confusion between the W that I'm using for my unit versus the W that I'm using for work versus the W that I use for weight. So again, it is very helpful to understand the concept and the context of the question or problem that you're solving, because we're using a lot of the same variables or letters to mean different things. So they show you in the bottom how we convert from our English unit into our SI unit. 1 horsepower, which is the English unit for measuring power. 1 horsepower equals 746 watts. So how does your Hemi, what does your Hemi do in SI units? 1 horsepower equals 746 watts. And you can figure out, you could go look up the specs for your Hemi and convert that from horsepower into watts. And it shows some energy conversion in humans. Again, I'm not so much interested in that, but this whole idea of metabolic rate, like that's important for like dietitians when they're helping patients to regulate their intake, or for whatever reason, or let's say if you're an athlete, these kinds of things are important. And then they go into some historical use of energy, projected use of energy. Here we are in 2020, and we're using 654 times 10 to the 18 joules of energy in that year. And they projected that we use that amount in 2020. That's quite a bit. And then they talk about the power consumed in different countries. So they're doing this per capita. This is a big word these days in talking about the COVID-19 virus, this per capita. And here in this graph, they're looking at the power consumption in kilowatts per capita. And you can see that Japan, in this particular graphic, Japan is just a bit ahead of us in terms of the power consumption per capita. So that's pretty much what I have for you today. What I'm going to do now is I'm going to unmute my screen, and I'll answer any questions that you might have. Just simply unmute your mic, and I'll be happy to address your question. Okay, I'll take the silence as nobody has a question. If you don't have any questions for me, you're free to leave. If you do have a question that you want to ask me on an individual basis, please hang around. I'll be happy to answer it for you.
Have a nice weekend.
You do the same. We're done, folks. Take care. Hunter, Robbie, do you have questions for me? If not, we're done. Hello? Are y'all paying attention? Hello? One last time. Do you have any questions? If not, I'm going to hang up.